Many financial technology systems carry a built-in defect. The application logic is baked directly into the gears of the ERP. When logic is inseparable from the legacy system of record, the entire application becomes brittle and resists scaling. Localized banking formats and global compliance rules intensify this rigidity. Engineers often have to build hundreds of fragile point-to-point data pipes just to keep regional variations from breaking the core system. True agility requires a framework called BAI independence. We need a system that functions regardless of the specific business, ERP, industry, or country context it operates in. A BAI independent system extracts every logic, data, and presentation layer out of the ERP and moves them into a standalone execution engine. Real enterprise flexibility comes from completely decoupling the accounts receivable workflow from the ERP's underlying structure, rather than simply upgrading the software. We are going to architect a decoupled, AI-driven cash application from first principles. We call it BAI CashApp. To build this, we'll use the BTF framework, defining the business, technology, and functional specifications required to make the engine run. Every architectural dimension we build today will be documented as a normalized relational table. These tables serve a specific role in deployment. They dictate exactly how the final product will function in a live environment. Forcing architecture into strict tabular formats is the necessary step to eliminate the data loss that usually occurs between a conceptual design and the final engineering build. System independence begins by standardizing core data taxonomies at the business layer. This is the MD CashApp table. Standardizing reason codes here decouples dispute workflows from proprietary legacy ERP deduction codes. We then layer on activity data and logics data tables, specifying where transaction records live and how algorithmic rules govern them. The logics layer's auto-matching algorithm scores match probabilities based on historical weights, operating independently of the system of record. We also include dynamic tolerance rules. If a payment is slightly off, the logic automatically clears the discrepancy, removing human intervention. By stacking these tables, we've built a self-contained brain that can evaluate financial transactions before the ERP even knows the cash has been received. Now we move to the technology domain to establish the infrastructure required to support this decoupled logic engine. The DI CashApp table outlines the foundational compute requirements. It prioritizes containerized orchestrators and event-driven brokers to handle millions of transactions with minimal latency. Security and compliance are built directly into the stack through the SP CashApp table. As banking data flows in, the tokenization engine masks sensitive account numbers and personal identifiers. Anonymizing this data at the gate ensures that our machine learning models train only on secure, non-sensitive financial patterns. This setup creates a fortress around the logic, ensuring global data sovereignty while allowing the engine to scale elastically. In the functional domain, we focus on how human operators interact with this automation. We use a model called DCID, Decisions, Data, and DViews. This replaces traditional ERP screens with context-aware micro front-ends. The DView match interface uses a split-pane workspace. It presents the unapplied receipt alongside AI-predicted matches, ranked by visual confidence scores. This reflects a principle called zero-state gracefulness. A highly automated system should present an empty workspace to the user, rather than a cluttered list of result items. When an AR specialist manually overrides a low-confidence match, the system captures that decision to update the machine learning feedback loop. Users don't need to pause to train the AI. The system learns directly from the way they perform their daily tasks. These DViews merge human intent with machine calibration, creating a system that improves its own accuracy with every click. We can stress test this model by tracing a complex transaction through our day-in-the-life process flow. First, an unstructured email with a short pay remittance enters the ingestion pipeline, is tokenized, and sent to the logic engine. The NLP engine scans it but fails to reach the confidence threshold for a straight-through match, diverting the packet to an exception queue. The packet appears in the DView Resolve workspace. A human resolver reviews the dossier and validates the short pay. Once validated, the technology data layer fires an outbound webhook back to the ERP, closing the open item in the system of record. This lifecycle proves the BAI independent architecture can handle everything from ingestion to human resolution and final ERP synchronization. Most architectural blueprints fail during the engineering handoff. This is known as translation loss. When developers receive static PDFs or wiki pages, the nuances of a decoupled model are often lost or hard-coded incorrectly. To prevent this, we forced every layer of our BAI CashApp design into a normalized tabular format. We prioritize machine readability over simple human legibility, ensuring the architecture can be understood directly by a processing engine. This leads to the final layer of our architecture, Table OS. The master data, logics, and infrastructure tables we've built are native relational nodes ready for instantiation. Just as a C compiler abstracts machine architecture to build platform-independent software, Table OS abstracts enterprise processes into tabular code. As Table OS ingests these matrices, it dynamically renders the UI and provisions the data pipelines without human engineering intervention. We have successfully used these structural requirements to define the executable source code for a universal cache application. In a truly weakly decoupled enterprise, the structural blueprint becomes the functional engine once compiled through Table OS.